Hi everybody! So in today's video, we're going to be looking at applying the mean value theorem to justify our conclusions or draw conclusions over a given interval. Now, what we did in our previous lesson was sort of introduce the theorem. We're going to go back over what the theorem says one more time, and then we are going to look at some example problems today. So as a reminder, the mean value theorem has two parts, the conditions and the conclusion. The first condition is that our function needs to be continuous on AB. As a reminder, that means no jumps, holes, infinite discontinuities, including endpoints. We also need to have a function that is differentiable. So that means that there's no corners, cusps, vertical tangent lines, or discontinuities, except possibly at the endpoints you could have like a corner or something, because we're not going to go beyond that. And if we meet both of those conditions, we get to say this really cool thing, which says that the slope of the tangent line at C, some value, has to be equal to the slope of the secant line between the endpoints. So to visualize this, if we look at this graph and we choose to look between, for example, -2 and +2, then the secant line would be the slope that connects these 2 points by just cutting through the graph. And the tangent line would be the places on the graph that have the same slope. In other words, it would look parallel when you graph it. It looks like there's going to be one spot right about here and another spot right about here. Okay, that's kind of the brief review that was in detail in the notes we took previously. I just wanted to go through it one more time. Now, here are the steps for applying the MBT. First, you need to verify that the function satisfies the conditions. So before you do anything, make sure you have a continuous and differentiable function, or else all bets are off. You can't promise anything. Then find the derivative and substitute the value x equals c into that derivative. So you want to find a c value, so make it a c instead of an x. Then find the average rate of change, or in other words, f of b minus f of a all over b minus a over the given interval. And lastly, set them equal to each other and actually solve the equation. Now we're going to go through this a couple different times, and I want to also show you a visual representation so that you can kind of see it in action. So first, let's verify that x cubed minus 3x plus 2 satisfies the hypothesis, which is the conditions, and then find all of the values of c that satisfy the conclusion. So symbolically, number one, f of x is continuous and differentiable because it's a polynomial. So it doesn't have any corners, cusps, vertical tangent lines, discontinuities of any kind. Step number 2 is to find the derivative and plug in the value c. So f prime of x is going to be 3x squared minus 3, which means if we change this to a c, we're going to have 3c squared minus 3. Step number 3 is going to be to find the average rate of change on this interval. So in other words, we want to do f of 2 minus f of negative 2 all over 2 minus negative 2. Now remember, we're doing f of 2, so not f prime. So we're going to go back and use the original equation here. F of 2 would be 8 minus 6 plus 2, which means we would have 4. minus f of negative 2 would be negative 8 plus 6 plus 2, which would be 0, all over 4, which is 1. Step number 4 is to make these things equal to each other and solve. So I'm going to make an equation using 3c squared minus 3 and 1. 3c squared minus 3 equals 1. To solve this, I'm going to go ahead and add the 3 to the other side. So I would have 3c squared equals 4. I'm going to divide, so c squared equals 4/3, which means c equals plus or minus the square root of 4/3. Now, just so that you can visualize this, I am going to go ahead and type this in and get a decimal. So the square root of 4/3 is 1.15. So in other words, it's going to be plus or minus 1.155. Here's what this looks like visually. Our endpoints are negative 2 and 2. The slope of our secant line is 1, which makes sense because if you connect the dots here, you're going to see that the slope of this orange line is 1. It goes up 1 over 1, which means the places on the graph where it has a slope, the derivative has a slope of 1, are at 1.1 and negative 1.1. And if you draw the tangent lines there, they look about parallel. It's also the same two places that we found just by a visual inspection when we were kind of estimating up here. So you'll notice like it's all kind of intuitive, but now we're able to find those values exactly and know exactly what x values to draw those tangent lines at. All right, let's take a look at problem number 2. So find the value of c that satisfies the mean value theorem. First of all, this is a continuous and differentiable function. And I know this because sine of x doesn't have any jumps, holes, discontinuities, corners, cusps, vertical tangents, anything like this. So it is continuous and differentiable just because I've graphed it before. I know what it looks like and it's not going to have anything weird going on. Second step is going to be to find the derivative and plug in c. So f prime of x would be cosine of x, which means f prime of c would be cosine of c. Step 3 would be to find the average rate of change. So we're going to need to do f of pi minus f of 0 all over pi minus 0. Now again, we're going to use the original function here. So sine of pi is 0. Sine of 0 is 0 all over pi, which means I get 0. And then we're going to go ahead and make an equation. So we're going to let cosine of c be equal to 0, and we're going to solve. If I think about the unit circle, the places between 0 and pi, where cosine is 0, is at pi over 2. So that means that the c value is going to be pi over 2. If you visualize a graph here, it also makes sense. So the graph of cosine, pi over 2, pi, 3 pi over 2, 2 pi. The graph of cosine starts high. Let me see here. High, middle, low, middle, high. So it goes like this. The secant line that we're looking at goes from 0 to pi. So we're talking about... Oh, I'm sorry. I should have graphed sine. Oh my gosh, you guys, I am so sorry. Bloop, 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 bloop. The original function here was sine, not cosine. Ignore what I just did. It goes middle, high, middle, low, middle. Oh, this is going to be a terrible example because now it's all messed up. I'm so sorry. If you look at from 0 to pi, it's going to be a horizontal tangent line, and it makes sense that at pi over 2, that would be parallel, another horizontal tangent line. I am so sorry about that, my friends. I stopped and I looked at it. I was like, something is wrong here. All right, now the next question is going to be explain why the mean value theorem does not apply to the function on the given interval. So what we need to do is figure out which of the conditions are broken. Is it not continuous? Is it not differentiable? If we think about this first function, what I'm noticing is I have this rational exponent here. So I'm thinking there's going to be something going on with that piece of it. I know that it's continuous because I can plug in 0, I can plug in -1. There's no problem with plugging in numbers, but I'm thinking something weird is going on with the derivative because I know that rational exponents often give me vertical tangent lines or cusps. So I'm going to go ahead and take the derivative. Now, when I do that and I rewrite the problems that I've got instead of a negative exponent, I'm just going to drop it to the bottom. I'm going to notice that I can't plug in 0. Because if I did that, I'd have a 0 in my denominator, which is not allowed. So because of that, and because the 0 is in between -1 and 1, we've got a problem. We're not differentiable. The derivative doesn't exist. So we would say that this function is not differentiable at x equals 0. Now, in the next problem, I've got a rational function. So right away, I know that there are certain numbers I can't plug in. I cannot let x be -1 here because if x is -1, it's going to be undefined. I'm going to have some sort of vertical asymptote. Since the number -1 is in between -2 and 0, this is a function that's not continuous. So I'm not continuous at x equals -1. Again, if it's an issue, like if your equation has an issue, then it's a discontinuity. If your derivative has an issue, then it's a differentiable issue. For problem number 5, this is a perfect example of something that has been on the AP test many times. It says applying the mean value theorem to g of x on 0 to 2 guarantees that there exists some value c such that g prime of c is equal to what? Well, in order to do this, we don't need to check the conditions because it already says we're applying the mean value theorem, so we must have met the conditions. We also don't really need to find the derivative because it doesn't say find the value of c, it just says the g prime of c has to be equal to. This is a perfect example where all you really need to know is the conclusion. The conclusion is that it has to be g of b minus g of a all over b minus a. That's the second part of the conclusion. If you look back at the original theorem, f prime of c has to equal f of b minus f of a over b minus a. In this case, it's just g. So g prime of c has to equal g of b minus g of a over b minus a. I'm just going to go ahead and find that, and then that's going to be my answer. So that means in this problem, I'm going to have g of 2 minus g of 0 all over 2 minus 0. G of 2 would be 3 times 4, which is 12, plus 4 more is 16, plus 1 more is 17, minus G of 0 is 1, all over 2. So I'd have 16 over 2, which is 8, and that would be my answer. All right, that's it for today. Thank you guys so much for watching, and I'll see you for some practice soon.